The chapter name is bending moment and shear force. So in bending moment and shear force, first we will see what is beam. Beam is what? It is the horizontal structural. Beam is a horizontal structural member which is normally subjected to a transverse or a perpendicular load. That is called beam. Beam is what? Beam is a horizontal structural member which is normally subjected to a transverse or perpendicular load. Now see this figure here. This figure shows this is the horizontal structural member here. This is the horizontal structural member which is subjected to this transverse or perpendicular loads here. So these are transverse or perpendicular loads which are acting on this horizontal structural member. So this horizontal structural member is subjected to these transverse or perpendicular loads. So this horizontal structural member is called beam here, and these are the two supports. These are the two supports of this beam here. So this is this support which is on the left end, and this is this support which is on the right end. Next concept is span. Span is what? The distance between the two supports. This distance is called as span of that beam. The distance between the two supports is called span of the beam. So this is the basic concept of beam here. Again, see here, what is beam? Beam is a horizontal structural member which is normally subjected to transverse or perpendicular loads. We are seeing in this figure here, this is beam here, which is horizontal structural member on which there is a transverse or perpendicular loads are acting. These are the two supports of the beam. One is on the left end, one is on the right end. Next concept we are seeing, that is span. Span is what? It is the distance between the two supports of the beam. That is called span of that beam. So this is the concept of beam and the span of the beam. Next is types of beam. So first type of beam is simply supported beam. So what is simply supported beam? When a beam is simply kept on supports, then those supports are called as simple supports, and the beam is called as simply supported beam. When a beam is simply kept on supports, then those supports are called simple supports and the beam is called as simply supported beam. For example, you can take poles of sheds. So the poles of the sheds is the best example of simply supported beam, where this is pole here which is just kept on these vertical two poles here. So this horizontal pole is called as beam, and these are the two vertical poles here. These are the two vertical poles. These two poles are the supports here of this beam. So as this beam is simply kept on these two supports here, that's why this beam is called as simply supported beam, and these two supports are called as simple supports. Next point in this, as this beam is simply kept on these two supports here, so these two supports, they will oppose to the weight of this beam here. So when these two supports opposes to the weight of this beam here, then these two supports, they will offer the reaction. They will offer the reaction, and this is the direction of the reaction offered by these two supports, where this direction shows that these supports, they are opposing to the weight of the beam. So that we can draw the simply supported beam as, see here, this is the beam here, and these are the two supports of the beam here, and these are the reactions offered by the supports here. If we take this as end A and this as end B, then we can write the reaction offered by the support at end A is RA, and the reaction offered by this support at end B is RB. So RA and RB are the reactions offered by the supports. So this is all about the simply supported beam. The second type of beam is the fixed beam. So what is fixed beam? When a beam is firmly built in supports, then that supports are called fixed support, and the beam is called as fixed beam. When a beam is firmly built in supports, then that support or those supports are called as fixed supports, and the beam is called as fixed beam. For an example, we can take a beam is firmly built into a wall or in a pillar. That is the example of fixed beam. When a beam is firmly built or firmly fixed into a wall or into a pillar. So this is the example of fixed beam. Now see here, this is the beam here, and as this beam is firmly built into this wall here, as this beam is firmly built into this wall here, then we can draw here a fixed beam as, this is the beam here, and this is the symbol of fixed support here. So this beam is now, we can call it as fixed beam here, and these are the two supports. We are taking the fixed support at left end, that is A, and the fixed support at right end, that is B. So these A and B are the two fixed support which is applied on this beam here. So because of that, this beam is called as fixed beam. Next is the reactions offered by this fixed support. Now see here, these fixed support, they are blocking or opposing the horizontal motion of the beam as well as vertical motion of the beam. So there will be a horizontal reaction at end A, there is a vertical reaction at the fixed support A. So we are taking horizontal reaction HA here and vertical reaction VA here. As this fixed support is also blocking the movement of this fixed beam here or movement of this beam, so we have to take the movement at this fixed support A, and as we are considering the clockwise movement as positive, so we will take here the clockwise movement here, and we are taking this clockwise movement as MA here. This is the movement at the fixed support A here. Then we can write here the reactions at the fixed support B here. So as this is a fixed support, so it will blocking the horizontal motion as well as vertical motion and the movement of this beam. So we have to take here first horizontal reaction, and this horizontal reaction we are taking it as HB. Then we will take the vertical reaction here, and this vertical reaction we will take it as VB, and then we will take movement. So as we are considering the clockwise movement as positive, then we will write here the clockwise movement, that will be MB. So these are the reactions offered by the fixed support, and this is all about the fixed beam. Next type of beam is, that is third type, is called roller supported beam. So what is roller supported beam? When a beam is supported by using roller, then that beam is called as roller supported beam, and the support is called as roller support. So when a beam is supported by using a roller, then the support is called as roller support and the beam is called as roller supported beam. For example, the roller which is used to roll the cricket pitch, that is the example of roller supported beam. Now see here, this is a beam here, and we are considering the left end of the beam as A here, and we are applying a roller support here, and this is the plane of this roller support which is horizontal here. Now see here, this beam which is a roller supported beam, it can having a translational motion. It can having a translational motion. It can also have a rotational motion, but it do not have a vertical motion. So the reaction which is acting on this plane of roller support, that should be the vertical reaction here, and this reaction, it will be perpendicular to this plane of the roller support. So perpendicular means it will have a 90-degree angle with respect to this plane of roller support, and we are considering this reaction as RA here. Now see here, if the plane of the roller support, if the plane of the roller support is inclined here, so this is the plane of the roller support which is inclined here, and this is a roller support which is applying on this beam here at end A of the beam here. Now this plane of the roller support, it will making an angle or inclination theta with respect to this horizontal. So the reaction which is acting on this plane of roller support, that should be always perpendicular to the plane of the roller support. So this reaction is perpendicular to the plane of the roller support, and this reaction we will take it as RA, and it is making an angle of 90 degree with the plane of the roller support. So this is all about the roller supported beam. Next type of beam is hinge beam. That is the fourth type of beam, which is hinge beam. Now see here, what is hinge beam? When a beam is supported by using pin. So this pin support is called as hinge support, and the beam is called as hinge beam. So when a beam is supported by using a pin, then that beam is called as hinge beam, and that pin support is called as hinge support. For example, we can take the push-pull doors. The push-pull doors are the best example of hinge beam, where the pin or hinge of doors, where the hinge or pin of door allows the rotational motion, Now see here, this is the beam here. We are considering this end as A here, and at end A there is a hinge support. Now see here, this hinge support will block the horizontal motion as well as vertical motion here. So the reaction which is offered by this hinge support, that will be, first is horizontal reaction HA, second one is vertical reaction VA. There will be a no movement here. Why? Because this hinge support, it will allow the rotational motion here. The hinge support always allows the rotational motion. Because of that, there will be a no movement offered by this hinge support here. So as there is a horizontal and vertical reaction which is offered by this hinge support, so the resultant reaction, that will be the inclined here, and we are taking this as RA, and this resultant reaction making an angle theta with respect to this horizontal reaction HA. So we can calculate this RA as, it will be square root of HA square plus VA square, and then we can calculate this theta as tan inverse of VA divided by HA. So this RA gives the magnitude of this resultant reaction at the hinge support, and this theta always gives the direction of this resultant reaction with respect to this horizontal axis. So this is all about the hinge beam. Next type of beam is cantilever beam. That is, fifth type of beam is cantilever beam. So what is cantilever beam? A beam whose having one end is fixed, and the other end is free. That beam is called as cantilever beam. For example, we can take steel bracket. So in case of steel bracket, the one end of the steel bracket is fixed in a wall here. So this one end of the steel bracket is fixed in a wall, and the other end of the steel bracket is free here. So the steel bracket is the example of cantilever beam, where one end is fixed in the wall and other end is free. Now see here, this is a beam here whose one end is fixed and other end is free here. So this is the cantilever beam here. We are taking this fixed end as A here. So we are already seen that there will be a horizontal reaction HA, there is a vertical reaction VA, and there is a movement that will be offered by this fixed support here, and this movement will be MA here. So these are the reactions offered by the fixed support. So this is all about the cantilever beam. Next type of beam is, that is sixth type of beam, is overhang beam. So what is overhang beam? Overhang beam is what? A beam is having some portion which is extended beyond these supports, that beam is called as overhang beam. For example, we can take a diving board of swimming pool here. So in case of diving board of swimming pool, what happens? Some portion of the diving board of a swimming pool is always extended beyond this support. So this is the example of overhang beam, which is diving board of swimming pool. So see here, this portion is extended beyond this support here. So because of that, this is called overhang beam, and we can call it as, it is a single ended overhang beam. If we draw a beam here which having these two supports, so here there are two ends. At the two ends of this overhang beam, which is extended beyond these two supports here. So these are the portions of this beam which is on the right side and on the left side, which are extended beyond these supports here. So this is called as double-ended overhang beam. So this is all about the overhang beam. The next type of beam is continuous beam. So what is continuous beam? When a beam is supported by using more than two supports, then that beam is called as continuous beam. So when a beam is supported by using more than two supports, is called as continuous beam. So these supports which are more than two, they may be same type, may be different types. So see here, for example, we can take the bridge is the best example of continuous beam, where there are number of supports, there are number of pillars which are supporting this bridge here. So as there are more than two supports here, so this bridge is what? It is a continuous beam, and this is all about the continuous beam and the types of beam. Next is types of load. So first type of load is concentrated or point load. So see here, what is concentrated or point load? A load which is acting at a particular point on beam, that load is called as concentrated or point load. Now see here, this is a beam here and these are the two supports of the beam. Now see, this is load W1 and this is load W2 which is acting on this beam. So these two loads are acting at a particular point on this beam. So the load W1 and W2, these are the concentrated or point loads. So these two loads W1 and W2, they are acting at a particular point on the beam. That's why the load W1 and W2, these are the point loads. So this is all about the concentrated or point load. The second type of load is called uniformly distributed load. This is also called as UDL. Now see here, what is uniformly distributed load? A load is uniformly spread over the span of a beam. Then that load is called as uniformly distributed load. A load is spread or is uniformly spread over a span of a beam. That load is called as uniformly distributed load. Now see here, this is a beam here who's having these two supports here, support A and support B here, and we are considering the small l is the span of the beam here. Now the load is uniformly spread over the span of the beam, then this load is called as uniformly distributed load. We are considering this as small w per unit length is the UDL, that is uniformly distributed load. Now next is we have to convert this uniformly distributed load into a point load. Now see here, we will draw this beam as it is. This is end B, there is a support at end B. This is end A, there is a support at end A, and this is the span of the beam, that is small l. Now we have to convert this uniformly distributed load into a point load or concentrated load. So first of all, we will find out the magnitude of the point load, and that should be always equal to the product of the magnitude of UDL and the span over which the UDL is acting, and that span is L. So W into L is the magnitude of point load. Now we will find out the position of this point load on this beam here. So see here, the UDL is acting over the span L of the beam. So we are dividing this span over which this UDL is acting by 2. So it will be L by 2 from end A, and it will be L by 2 from end B, and this is the position of this point load. So this is the procedure to convert the uniformly distributed load into a concentrated or point load. So this is all about the uniformly distributed load. Next is shear force. So what is shear force? Shear force at any section, shear force at any section of a beam is the algebraic sum of all the vertical forces, algebraic sum of all the vertical forces which are acting on either side, of a section of beam. That is, shear force. The shear force at any section of a beam is the algebraic sum of all the vertical forces which are acting on either side of a section of a beam. So that either side, it will be the left side of a section of a beam, or it will be the right side of a section of a beam. Now we will see this sign convention for shear force. Now see this sign convention for shear force here. When the vertical force which is acting on a left side of a section is in upward direction, see this, is in upward direction, and the right side of a section, the vertical force which is acting in downward direction, then the shear force will be considered as positive. Again see here, when the vertical force which is acting on the left side of a section, see here, this is a section here, and this vertical force which is acting on the left side of a section is in upward direction, and the vertical force which is acting on this right side of this section here, which is acting in a downward direction, then the shear force should be considered as positive. And see here, when shear force should be considered as negative, so see this is a section here, and the force, vertical force which is acting on the left side of a section is acting in the downward direction, and the shear force which is acting on the right side of a section which is acting in upward direction, then the shear force should be considered as negative. Again see here, when shear force should be considered as positive, so this is a section here, on the left side of a section, when the vertical force which is acting in upward direction, and on the right side of a section the vertical force which is acting in downward direction, then the shear force should be considered as positive. And when the vertical force which is acting on the left side of a section is acting in downward direction, and the vertical force which is acting on the right side of a section is acting in upward direction, then the shear force should be considered as negative. So this is all about the sign convention for shear force, and this is the concept of shear force. Next is bending moment. What is bending moment? The bending moment at any section, the bending moment at any section of a beam is the algebraic sum of moments of all the vertical forces, moments of all the vertical forces which are acting on either side, of a section of beam. That is bending moment. So what is bending moment? Bending moment at any section of a beam is the algebraic sum of moment of all the vertical forces which are acting on either side of a section of a beam. So that either side, it will be left or right side of a section. Next we will see the sign convention for bending moment. Now see here, first we will see the positive bending moment. Now see this section here, this is a section here, and if the movement of the vertical force on the left side of a section is clockwise, or the movement of the vertical force which is acting on the right side is anti-clockwise, then the bending moment should be taken as positive bending moment, and this positive bending moment is also called as sagging bending moment. Now see here again, if the moment of vertical force which is acting on the left side of a section is clockwise, or the moment of vertical force which is acting on the right side of a section is anti-clockwise, then the bending moment should be taken as positive, and this positive bending moment is called sagging bending moment. Now see here, what is negative bending moment? So see this section here, and if the moment of vertical force which is acting on the left side of a section is anti-clockwise, or the moment of vertical force which is acting on the right side of a section is clockwise, then the bending moment should be taken as negative bending moment, and this negative bending moment is also called as hogging bending moment. See here again, if the moment of vertical force which is acting on the left side of a section is anti-clockwise, or the moment of vertical force which is acting on the right side of a section is clockwise, then the bending moment should be taken as negative bending moment, and this negative bending moment is also called as hogging bending moment. So these are the sign conventions for the bending moment, and this is all about the concept of bending moment. Next is the relation between shear force and bending moment at a section. Now consider a beam AB here. See here, this is beam AB which is having span of capital L here, and over this beam AB the UDL of W per unit length which is acting over the entire span of this beam AB here. At end A and at end B there are two supports here which having reactions RA and RB. So RA and RB are the reactions at supports at end A and at end B. Now considering a small length dx of a beam between section P and Q. Now considering the small length dx, or we can say delta x, considering a small length delta x between the sections P and Q. So between the sections P and Q there is a shear force and bending moments are shown here. So see here, we are considering a positive shear force and positive bending moment. So because of that, at section P we are taking the shear force F, at section Q we are considering the shear force F plus delta F, and at section P we are considering bending moment capital M, and at section Q we are considering bending moment M plus delta M. So these are the positive shear force and bending moment at these sections P and Q. Now we are taking the element between this section P and Q, this element which having length of delta x, this element between section P and Q is in equilibrium. So as the element between section P and Q is in equilibrium, then the shear force and bending moment, the shear force and bending moment, they are also in equilibrium. So as the element between sections P and Q is in equilibrium, then the shear force and bending moment, they must be in equilibrium. Now we are applying this summation of Fy between this section P and Q here. So if we apply summation f of y between section P and Q, why we are applying summation f of y? Because in section or in between section P and Q, all the forces are vertical forces. Because of that, we are applying summation f of y between the section P and Q here. So summation f of y should be equal to, we have to take this force F as minus of F because it is acting in downward direction, then minus of W into delta X. This is the force which is acting in a downward direction of the UDL. Then we will take the force F plus delta F as positive here. The force F plus delta F as positive. Why? Because it is acting in upward direction. So these are the forces which are acting in between section P and Q. Now we are applying condition of equilibrium here. So summation f of y is equal to 0 is equal to minus of f minus w into delta x minus w into delta x plus f plus delta f. Now this minus f and plus f, it will get cancelled here. So we can write here 0 is equal to minus of w into dx plus df. Now we are shifting minus w into delta x on left side, so it will be plus of w into delta x is equal to delta f. Then we can write here delta f divided by delta x is equal to w. So from this we can write here the rate of change of shear force, that is delta F by delta X is equal to the rate of change of shear force, that is delta F divided by delta X is always equal to the intensity of loading, on the beam, and that intensity of loading on the beam, that should be W here. So the rate of change of shear force, that is delta F divided by delta X, is always equal to the intensity of loading on the beam, and that intensity of loading is W. Next we will take the moment about point Q, and the moment about point Q in between section PQ. Then we can write here the moment of this force F, that should be in anti-clockwise direction with respect to this point Q. So we can write it as minus of F into the perpendicular distance is delta X. Then we will take the moment of this UDL, and moment of this UDL will also in anti-clockwise direction with respect to point Q. So we can write here minus of W into delta X is the force, but we have to take the perpendicular distance of this, the UDL, moment of the UDL from the point Q here, and that should be equal to delta X divided by 2. So W into delta X is the force, and delta X divided by 2 is the perpendicular distance of this force W into delta X of the UDL from the point Q. Then we will take the moment of this F plus dF, but F plus dF, this force, it is passing through the point Q here. So because of that, the moment of this force F plus delta F is equal to 0. Then we will take these two moments here, M and M plus delta M. The moment M, it will be clockwise with respect to point Q here. So we will take it as positive, and the moment at point Q, that is M plus delta M, with respect to point Q, it will be in anti-clockwise direction. So we will take it as negative. So it will be minus of M plus delta M. Now we will take the condition of equilibrium. So if we take the condition of equilibrium, then the algebraic sum of moment about point Q is equal to 0. So 0 is equal to minus of F into delta X minus of W divided by 2 delta X square into delta X into delta X, it will be delta X square plus of M minus of M minus delta M here. So this plus M and minus M will get cancelled here. So we can write here 0 is equal to minus of F into delta X minus of W by 2 delta X square minus of delta M. Now as delta X is very small, so delta X square is neglected here. Delta X square is neglected. So as delta X square is neglected, then we can write 0 is equal to minus of F into delta X minus of delta M. So we can write here delta M. If we shift this minus delta M on left side, then it will be plus delta M is equal to minus of F into delta X. So we can write delta M divided by delta X is equal to minus of F. So this is the rate of change of bending moment. This delta M divided by delta X is what it is, the rate of change of the bending moment, and this rate of change of bending moment is what it is, delta M by delta X. It is always equal to the shear force, and that shear force is F here. So the rate of change of bending moment is always equal to shear force, that is delta M divided by delta X is equal to minus of F, and this is the relation between the shear force and bending moment at a section, and this relation shows that the rate of change of bending moment is always equal to shear force. So this is all about the relation between shear force and bending moment at a section.